it's the same thing you took a quiz on, which again, the quiz results are in the grade book already. You'll see them tomorrow. It's the same thing, but now just with word problems. It's applications, applying a linear, either linear, quadratic, or exponential model wherever it would be needed. So let's see, which of the following would best be modeled by linear, quadratic, or exponential? A window cleaner is cleaning windows about halfway up the Peachtree Plaza Hotel in downtown Atlanta. The cleaner did not properly clip one of the squeegee tools, and it fell from 400 feet up in the air. The height of the squeegee, t seconds after it fell, is given below. What type of function, linear, quadratic, or exponential, would best describe the squeegee's height as a function of time? I mean, if you know anything about physics and stuff, you wouldn't even have to look at this. You should already know at least what type it is, but if you don't, let's just before I get into specifics, I just want to give you a quick little lesson on something. What do we call a measurement that relates? Better yet, what is height a type of? What type of measurement is height? No. What type of measurement is height? Well, height can be measured in feet. What else is measured in feet? Or inches, or miles, or meters? Distance, very good. Height is a type of distance. Okay, so what type of measurement is a comparison or a ratio, if you will, of distance and time? Speed, yeah. So what we're doing here is measuring throughout different times the speed of this squeegee. Okay, now here's where the physics comes in. Maybe you've heard of this, maybe you haven't. When you drop an object from any type of height, is the speed in which it falls constant? Is it always falling at the same speed? No, it is accelerating. What is causing it to accelerate? Gravity. Does anybody know what the and this one I might be wrong. I'm gonna write what I think I remember, but I'm not a physics teacher, so I might be wrong on this. Does anybody has anybody ever learned before in maybe like in a science class what the acceleration due to gravity is on a free? Yeah, very good. It's about 9.81. I believe it's meters per second squared. Pretty sure it's in meters. 9.81 meters per second squared. Now here we're measuring in feet, but the point is that not only is the height changing, the speed is changing. So if something is not only if an object is gaining speed, so like not only is the height changing, but the height is changing faster and faster and faster and faster. Before we even go look at the numbers, which one of these would you expect it to be? Yeah, it's probably going to be exponential. Let's see. I do not see a common difference. And if I don't see a common first difference or second difference, that basically eliminates linear or quadratic. Now, with linear, we should assume that, sorry, not with linear, with exponential, there should be a common ratio that's geometric, but sometimes that could be affected by the location of an asymptote. So let's just check here. This is 384 divided by 400. This would be 336 divided by 384. This would be 256 divided by 336. This would be 144 divided by 256, and then finally at the end, well, 0 divided by anything is 0. So let's you're probably going to get decimals, but let's just see what those decimals come out to. Divided by 4. I got here 0.96. 336 divided by Here I got 0.875, 256 divided by 336. Here I'm getting 0.76. And finally, 144 divided by 256, 0.56. So those aren't all the same, but again, that could be just affected by the by the where an asymptote would be. Let's see, if we're measuring height, see how this would look like. So here's time. Time can't be negative. This thing fell, and as it's falling, it's falling faster, so it looks something. Yeah, that's the thing. The thing is that the asymptote is going to be up at the top. It should be looking. It is decreasing, but at an increasing rate. The other word I'm picking up on is here is best. What would best describe it? So even though we can't prove necessarily that it's exponential, based on the values that we're being given, that's the only one it could be. I don't see that it's asking you for anything else. Read, is that confusion? You don't understand exponential? The only other way I could describe it is, okay, look at the y's. Again, like we can't prove that it's exponential, but look at the y's. Do they ever change direction? Like from the first y to the second y, is 384 less than 400 or more than 400? 384 is less, right? And as we go to the right, you're always getting less, 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 less. Okay, so it can't be quadratic. Like that we know for sure it can't be quadratic, because quadratic, yeah, if you were going down, then you'd have to come back up if you were going to be quadratic. Okay, so it can't be that. So the only thing it could be is linear or exponential. Now, I tried to give you a background on acceleration due to gravity just to show you, hey, it's probably not going to be linear. But if it were linear, if it were to be linear, for sure what would have to happen is we'd have to have a common difference. And here we don't have a common difference. So like from here to here is minus 16. This is minus, I think, 48. This would be minus 80. Minus 80, I think, minus 80. That would be minus 112, minus 112, and then this is minus 144. The first difference is nowhere near common. So because the differences are increasing every time, it's not just that it's decreasing, but it's decreasing by more and more each time. The only one that it could be is exponential. Does that make any sense? Okay. Joey's shower fixture began leaking water, so he called the plumber to help him fix the problem. The plumber said he would charge $100 for making a house call and $60 for every hour that he's working. What type of function would best describe the amount the plumber charges? I already kind of have an idea what this could be because I'm used to writing work columns before, but before we look at the numbers, does anybody have an idea what we'd be looking for first? If we want to know what would best describe the charge, would it be linear, exponential, or quadratic? I would probably say linear because I could tell, and this is the way a lot of price structures are made up. He's charging $100 just for showing up. That's a flat fee. But then any remaining cost is going to be directly related to the hours. $60, $60, $60, $60. What could we call that $60? There's two things. You could call it the slope. That's very good. But you could also call it the common difference. Very good. And sure enough, when we do it, we have plus 60, plus 60, plus 60, plus 60. This definitely ends up being linear. You know what? Let me write these down. So the first one, exponential. Second one, And then C, please don't put quadratic just because of process of elimination. Let's actually read it. A pot of tea was brewed so that the temperature was 200 degrees Fahrenheit, and then the stove was turned off. The pot of tea slowly cooled back to room temperature at 80 degrees Fahrenheit over a few hours. The data shown below in the table. What type of function could it be? Well, okay, I really don't have um, a predisposition to leaning one way or the other. I would think it's not going to be exponential because unless something is like unless you maybe stick it in a refrigerator or something that's going to be rapidly cooling it, then maybe it could be exponential. But I'm doubting it's going to be exponential. Now, when you turn off the, does it say when we start counting? Uh, Yeah, it doesn't really say, but from what we're reading, I'm assuming that we started counting time from the time that the stove was turned off. Okay, so from the time that you turn off the stove, do you ever like expect the pot of coffee to start cooling, 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 and then heat up again, but then cool again? No. No, it's probably going to go one way or the other. So if anything, by process of elimination, I'm kind of leaning towards linear. It should be linear because remember quadratics change direction, but let's see. Could be wrong on this one. Let's see. This is minus 60. This is minus 50. No, minus 30. That might be wrong. It might be exponential. Minus 30. Minus 15. Is it going to be quadratic? Not quadratic now. 30 now. And then minus 7.5. So is it linear? No, and we already kind of explained why it wouldn't be quadratic. But if you want to verify why it's not quadratic, then this is plus 30, plus 15, and plus 15, and then plus 7.5. So it's not. So it looks like it is going to be exponential. It's going to get cooler faster. You could take a look at that also by checking to see if there's a common ratio. So this would be 140 divided by 200, 110 divided by 140, 95 divided by 110, and 87.5 divided by 95. This cancels out. 14 divided by 20 is 0.7. .10 divided by 140 is 0.78. 95 divided by 110 is 0.86. And then 87.5 divided by 95 is 0.92. So even though we don't have a common ratio, we see that the ratio though is increasing. Like the temperature is decreasing, but at an increasing rate. Every time that it's decreasing by more. Actually, no, sorry, the converse. It's actually decreasing by less because the next temperature is a bigger percentage of the temperature before. Yeah, the only one this could be is exponential. It has to be exponential. If there isn't a common difference or a common second difference, it has to be. Jason, you got that? All right, let's move on to the next one. Which of the following would be best modeled by each function? A company named Phone Phase Foundry designs hardware for new smartphones and is offering a new employee an initial salary of $40,000 a year and will get a raise of an additional $6,000 for each year he works for the company. What type of function would best describe the employee's salary based on the number of years? And can you determine the function? Okay, let's do both. I think for this it would help you it would help you to actually write out the sequence. So let's see. Um, at 0 years, right when he first starts working for them, how much is he making? 40,000, right? But then, and then at the beginning of the first year, once he finishes a year, how much is he gonna? It would be 46,000. You know what we can just do, since it's all gonna be in thousands, we don't even need to put the extra zeros. We can just do 40, 46, 52. And that's not a bad raise too. 6,000 a year is pretty nice. Constant. 58. What is it? 64. Blah blah blah. So can we tell what type of model this is? If it's going up the same constant amount each year of 6,000. It's what? It is going to be linear. And then can we model this? So let's say A is the amount it makes. What's the initial amount he started making? Yeah, 40,000. And then how much is it going up each year? Yeah, now in this case though, since we knew how much he was making before any years passed by, there's no need for the n minus 1. So it would just be the 6,000 that he's making every year plus the 40,000 that he made originally. Because that 40,000 was before he started working, like from the first day that was his salary. A company named Phone Programming designed the software for new smartphones and is offering an employee 40,000 and will get a raise of 12% each year. Well, we've seen these problems before. We saw them when we were doing sequences. When something increases by 1%, what's it going to be? It was geometric, but geometrics are then exponential. Yeah, it's going to be exponential. X, Y, exponential. And can we determine the function? Sure. What's the initial amount? What's the initial amount? The same 40,000. What's the growth factor? Yeah, I mean, yeah. So like when we first started, like we had to build up on this, and I had to show you that it was 1 plus 0.12. I would hope by now you know it's just 0.12. And again, since this 40,000 was before he made anything, yeah, it would just be to the power of it. It wouldn't be an n minus 1. Which company will provide a better salary after 2 years of employment, and then after 8 years? So let's we would now plug in 2 and plug in 8. Let's do the first one, and let's do A at 2. So first one is 6,000 times 2. Gonna end up being 52,000. Second company after 2 years is gonna be 40,000. 1.12 times to the second power. No. It's just not bad. I already saw you working on your crossover. You need both feet to cross somebody up. Here I'm getting 50,176. So which company would be better to work for after 2 years? Yeah, the first company is better, and that was called Phone Phase Foundry. Phone Phase Foundry. Now let's do the same thing for 8 years. Is 6,000 times 8 plus 40,000. So that's what 48,000 and 40,000, that's 88,000. And then the other company, after 8 years, is 40,000 times 1.12 to the 8. Well, let's go to the nearest dollar. Let's round up to the salaries you don't get cents. So 99,039. Yes. Okay, just leave it there. Or leave it here. And you got one. Okay. So which company is better to work for after 8 years? The second one, yeah. Thanks, Michael. And that was called Phone Program Ring. Phone Program. That would be a great topic to stay with phones all day. Why don't you come and sit closer, man? Oh, Brandon, that's impressive, dude. You're in a circus. And that somehow makes you less tired the way you're sitting? You're using your legs as a pillow. Well, just don't do that, man. That looks painful. A student was marking the growth of a corn stalk and at least for the first several weeks the plant's height. And what could be described in the following model? What does the 5 represent? Okay. If they've already modeled it for you, we're not modeling. What does that 5 represent there? Good, because we're measuring height, so this is going to be the initial height. Initial height. What does the 1.40 represent? Yeah, that's the growth factor. The plant is growing. A person purchased a new car which depreciates in value. The owner determined the value of the car. Okay, blah, blah, blah. They've already modeled it for us. What does the 23,000 represent? Yeah, the purchase price of the car. Purchase price. That's how much you bought it for. What does the 0.93 represent? What does the 0.93 represent? The decay factor. I think we've also heard this, one of the sheets called this the split factor, even though it's not really splitting that. They use that more for half-life. Split in half, but decay factor. A physical therapist charges an initial fee and then charges another amount per hour. Okay, blah, blah. What type of function is that? The first two were exponential. What type of function is this? Yeah, this is linear. What does the 40 represent? Yeah, the per hour charge. Per hour fee. What's another word for that? That we've already said twice today. Slope? What's another word for it? Common difference, yeah. So there's a per hour fee. What does the 140 represent? Yeah, the initial fee. Okay, and then finally, for the first time today, I don't recall having seen anything quadratic so far today, but this one does appear to be quadratic. Show me that you remember something from the first semester. What form is that quadratic function in? Somebody not name it and tell me what form that quadratic function is in. Yeah, it is in vertex form. So what does the 2.4 represent? Well, okay, remember that a vertex, right, h comma k, that's really just the x and y of the vertex. So if we can figure out what's the x and what's the y we're measuring, let's see, the ball is struck, the height in feet of the ball can be described by the following function where the t is in seconds. So in this case, the x is the time and the y is the height of the ball. Remember that a ball follows a projectile motion, which can be described as parabolic. Okay, you can also tell by this that since we have a negative out in front, that's why it's an upside down facing parabola. So if the 2.4 right now is really acting as the h, and the h is just the x of the vertex, what is the x coordinate representing? Yes, good. So the 2.4, well, the x is representing time, so the 2.4 represents the time it took for the ball to reach maximum height. And what does the 70 represent? The 70 is the maximum height. But what we know is that due to vertex form, since we understand vertex form, this point here is at 2.4 comma 70. The 2.4 is how long it took to get there in seconds. The 70 is how high the ball got. Did I ask you to sit back in your seat? I didn't say please, pretty please. Presto, alakazam, go. Back to your seat. Anybody else? No questions? Nakai? Can you do what Brandon was doing? It's crazy. Create a function and model for each of the following. So some kids are selling lemonade for $1.50 per cup at a high school baseball game. They spent $14 on all the items needed for the lemonade. Create a function that represents their profit based on the number of cups that they sold. So this is going to model profit. Now, I guess maybe you need a little bit of an economics lesson here, but profit is equal to revenue minus your expenses. So how much you bring in minus how much things cost. So how much money are they bringing in? Yeah, 150 per cup. You don't need the zero, so 1.5, and then it is going to depend on cups sold. They spent $14 on all the items needed. So minus 14. And then if you were to take an economics class, then they would teach you like, how many cups do they need to sell to break even? You take that your senior year, economics. Yeah, I think that's what's next door. Economics. Hey, first year teacher, and well, hold on, let me just make sure. They weren't asking us anything else, right? There wasn't a follow-up question, it was just to write it. Create a function. Yeah, that's it. The first year teacher is paid $38,000. Each year, she is paid an additional 5% over the previous year. Create a function that would, okay, so yeah, 5% over. What type of a function is this going to be? Yeah, it's going to be, yeah, because that's the common ratio there. So let's just say the amount that you make is the first year, which is 38,000. What's the growth factor? 0.05. And then you can use N if you want. Let's use Y for years. Use T for time. Let's use T. Any questions there? I just think maybe we'll check the chance of finishing this one very fast. Comparing function types. A top level professional sports organization offers its athletes two different bonus retirement plans. In option one, they will start an account and add $20,000 years per year for each year the player plays successfully in the organization. And option two is they will start an account with $20,000 and add 50% to the value of the account for each year that they play. So, and you can see that kind of model there for you in the chart. Which option would be better for the athlete if he played for the team for 3 years? And how much is the difference between the three plans? Because they want to know 3 years, I'm already almost there. The next blank would be 3 years. Why don't we do, instead of finding this explicitly, let's just find it recursively. What type of a model is the first one? Yeah, this is linear. So it's a common difference. So the next, we're adding 20,000 here. So this is going to be 80,000. What type of model is the next one? When you're adding 50%. This is exponential because that's geometric, sure. And what we're doing there is multiplying by 1.5. Times 1.5 times 1.5 times 1.5. Don't tell me. 67,500. And would you agree with that? Would somebody put 45,000 times 1.5? So which one's better after 3 years? No, after 3 years? No, option one, the linear one. Better. And how much of a difference is there? There's a difference of $12,500. Which option will be best if there was 10 years? And then what's the difference? Well, since I don't feel like going all the way to 10, let's actually go ahead and write the explicit definition and then substitute. So the first one's linear, with the first amount being, now remember, be careful, because I know how much zero, like since I know the zero amount here, I do not need the n minus 1. I can just use n. So this is going to be how much we're going up each year. We're going up 20,000 each year, plus the original 20,000. That's the first one. The second one, it's 20,000 at the beginning, then the growing by 1.5 to the power of the number of years. So now let's find a sub 10 for each one. 20,000 times 10 plus 20,000. Luckily, 10 is an easy number to do mental math on. So 20,000 times 10 is 200,000 plus 20,000 is 220,000. 220. The other one I can't do mentally. So I'll use the calculator. It's sub 10, 20,000 times 1.5 to the power of 10. So let's go 1.5 power 10 equals times 20,000. I'm getting there. 1,153,000 301, depending on if you want to round up or down. So now which one's better after 10 years? Which one? The first one. You'd rather have 220,000 than 1,153,000? You're the one wearing the book bag, so what does that say about you? Oh, this class is fun. See, that's the dumbest thing you said all day. Nobody wants to leave here. And now let's subtract 1,153,301 minus 0, 0, 0. And not only is it better, it's better by 933,301. So like if you were like a running back, what would probably be the better option? No, probably the first one, because running backs don't last very long. But if you were like a kicker, what would probably be the best option? Yeah, because kickers can kick forever.
Like running backs.
Running backs do not last. That's like the average career of a running back is like maybe 3 seasons, if that. So don't play very long. Very few running backs play past the age of 30.
How Marshall Lynch?
How many Marshall Lynches are there? Two different computer programmers are trying to hack into a computer file that has been protected by an encryption key using a brute force method in which the computer begins trying all possible passwords. A company is going to what? That's not spelled correctly. It's higher, but it's that's bad. Higher. The programmer who successfully retrieves the file first. The first computer programmer, Bill, wrote a brute force program that will try 50,000 passwords each minute. The second computer programmer, Marcy, wrote an adaptive program that leveraged the hardware more efficiently and will try 5,000 passwords the first minute, 10,000 the next, 20,000, and then it just keeps on doubling. Which programmer will have tried the most passwords to break the code at the end of 5 minutes? And what's the difference? Well, luckily they give us that, and this is in thousands. So at the end of 5 minutes, this person has tried 250, and Marcy has had 155,000. So which programmer? It's Bill at the end of 5 minutes. And how much of a difference is there? It's going to be 95,000. That's better. 95,000. Which programmer will have tried the most passwords to break the code at the end of 10 minutes? And how much of a difference? Okay. Don't worry about doing the last one, because that's called a series. We haven't done, like, the easy way to do that is a series, unless you want to do it by hand. See, because the thing is, in this particular problem, if it was this that was most important, not a big deal. But the thing is that what's most important is the second, and that's the sum of the two. 10 plus 5 is 15, plus 20 is 35, plus 40, like how you have to add all the ones before, and that's called a series. We're not really doing series. Based on what we've learned about exponential functions, like here's what I guess what I would say is the most important. Based on what we learned about the way exponential functions work and linear functions work, like the second one is exponential because it's growing by a factor. It's growing by it's doubling, right? Wasn't it supposed to be doubling? Yeah. It's doubling. Whereas the first one is linear, which the further you get to infinity, okay, which 10 is closer to infinity than 5 is, which ones tend to grow much more faster? What's going to grow a lot faster, exponential or linear? Exponentials are going to grow faster. So I would assume the answer to the second one is going to be Marcy. Oh, I mean, well, do you want to do it recursively? We can do it recursively. I just don't want to do it explicitly because it's a different formula we haven't learned. It's called a series. If you were to do it recursively, you can just go like this is the difference here is 10 and 20. No, maybe you could. Oh no, hold on, we can do it. I'm trying to get out of here, but we can do it. But we'll just ignore the first the first row. Let's just use the second row. So Bill started off now because they're giving us the n is 1. We're gonna have to use n minus 1. So his amount after 10 minutes is the original, which is 50, plus the common difference. Now we're looking at the common difference here, but that's also 50 times 10 minus 1. So that's 50 plus 450, which is 500, and this is in thousands, so it's 500,000. Then for the second one, for Marcy, her original amount was 5. Her growth, what was the differences that were double? What was the numbers that were double? Just don't worry about it because it's not these numbers that are telling you. But just go one by one. Yeah, like because it's this is the number. See, this is 10, and then this is 20 more, and then 40 more, and then 80. If I gave you the formula for a geometric sum, you can do it in seconds, but you don't have that formula. So we can just go in. This would be 160, 320. This would be what is it? 640, 1280. Is that enough? Get there. We're going to be 6. 475. 2555 plus 2560. I'm getting, I'm not using the formula, just doing it recursively. I'm getting 51, 55. I'm doing some of it I'm doing mentally, but so I might be off a little bit, but it's still way more. When you have 1,000, that's a million, so it's a little bit over 5 million passwords. So obviously the exponential won't be fast. Not as fast as Caleb is on the court, but it's fast. Yeah.